Similarly, we have phase margin. So what is a phase margin? The amount of phase lag that can be added to the open loop transfer function, or that can be added within the loop, so that the phase of the system is equal to minus 180 degrees, which means the phase of the system will be at the verge of instability. How can you write the phase margin? Phase margin is 180 plus 5gc, where 5gc is the phase angle of gh of j omega at gain crossover frequency. So we have two crossover frequencies, omega pc phase crossover frequency used to find the gain margin of the system, and we have another frequency, gain crossover frequency, used to find the phase margin of the system. So when you look at this closed loop transfer function, so this is g of s, this is h of s, and the loop transfer function is gh. Now when you add these two gh transfer function, then look at this. So let us say the total gain of the system at phase crossover frequency is 3 and the maximum allowable is 6, then gain margin is 2, which means if at all if we add any element or any component in the loop as a compensator or controller, the gain of such element should not be greater than 2. This is what your design is. When you design such that the extra component when you introduce in this loop, its gain is not more than 2. So that is the importance of the gain margin. Similarly, what is the phase margin? The total phase angle should be 180 degrees. It is not more than 180 degrees. If it is greater than 180 degrees, the output will be out of the phase. The out of the phase can be taken as instability or unstable nature of the system. Therefore, if you take at gain crossover frequency, what will be the phase angle contribution of this g of s? What is the phase angle contribution of h of s? Then what is the remaining that is available to me? Let us say this takes 90 degrees, this take 70 degrees, then the remaining is 20 degrees is a phase margin. Whenever you introduce extra component in the system, the phase lag of that component at gain crossover frequency is not greater than 20 degrees. If it is greater than 20 degrees, this system will be out of phase, it is unstable. Then if within the 20 degrees, then system will be stable. So what we want is, we want more phase margin, so that even if you introduce a component which is having more phase lag, still you are within control. Similarly, when you introduce, if you have more gain margin, even if you add more gain to the system, amplifier gain, then we are in the still a stable condition. So ideally we say that we need to have more gain margin, more phase margin. But if you have more gain margin, more phase margin, there is another problem. The system response may be sluggish sometimes. So we have a certain range of optimal values. Say my gain margin is around 6 dB to 12 dB, and my phase margin is around 30 degrees to 40 degrees for optimum values when you are designing any system. Out of all the specifications we have seen, the first 4 are for the closed loop frequency response, and the next 4 are of open loop frequency response. So in general, using open loop frequency response, we are going to find the closed loop stability of the system, and also we are going to design for given specifications using this open loop frequency response. Now, so to understand this resonant peak, bandwidth, and also resonant frequency, let us look at this problem. The problem statement is like this. For a given control system, the damping ratio is 0.707 and the natural frequency omega n is 10 radian per second. Find resonant peak, resonant frequency, and bandwidth of the system. So in this case, the transfer function is not given, but the damping ratio and natural frequency both are given. So once these two are given, then we can easily substitute in the formulas available to find the given resonant peak and as well as the resonant frequency and bandwidth. The first one is resonant peak. So for second order system, because we have zeta and omega n, we can easily write mr is equal to 1 divided by 2 zeta under root 1 minus zeta square. So zeta is 0.707. If we substitute here 0.707 and root of 1 minus 0.707 whole square, and this comes around your mu r mr is equal to 1. So the magnitude is, the peak magnitude is 1 when zeta is equal to 0.707. So if at all if zeta is greater than that, then mr we cannot calculate. That means MP, percentage MP in time domain is for all the range of zeta values from 0 to 1, whereas in frequency response this resonant peak is valid for only 0 to 0.707, not more than that. Similarly, we can find out resonant frequency. Omega r is omega n into 1 minus 2 zeta square. When you substitute it, you are going to get it as 1.414 radian per second. Similarly, we have the bandwidth formula. Omega b is omega n into under root of 1 minus 2 zeta square, plus again we have one more root in under root inside, that is 2 minus 4 zeta square plus 4 zeta power 4. Then when you substitute the zeta value and omega n value, then you will get it as 10.1 radian per second. So this way we can easily find out these three important closed loop frequency domain specifications. Let us look at another problem on frequency domain specification. The problem statement goes here. The specification given on certain second order system is that the overshoot of the step response should not exceed 25%. Find the limiting value of damping ratio and corresponding peak response, that is peak resonance, and resonant frequency and peak time of the system. So in this problem we have a design specification in terms of time domain, that is peak overshoot. The peak over should be within the limit of 25%. So for that 25% we need to find out what is the damping ratio, and using the damping ratio then we can find out the other things which are asked here. Now, so the given overshoot is 25%. We know the formula for overshoot. So percentage MP is e power minus pi zeta divided by 1 minus zeta square into 100. So the given peak overshoot is 25%. You can substitute here 25% is equal to, then you can write the other time e power minus pi zeta by 1 minus zeta square into 100. So that goes 0.25 is equal to e power term. Then apply natural logarithm, because exponential term we have, you want to get that exponential term, then we use natural logarithm. So when you apply natural logarithm, and the natural logarithm of 0.25 goes minus 1.3862 is equal to whatever we have, the minus pi zeta by 1 minus zeta square under root. Then again if you rearrange terms, then pi zeta is equal to 1.3862 into under root of 1 minus zeta square. Then we can square both sides and you can simplify, then you can find out the zeta value. The zeta value is 0.4. So we know that when zeta is 0.4, the peak overshoot will be 25%. When zeta is 0.5, the peak overshoot reduces to 16%. So in this case for 25% peak overshoot, directly we can write down zeta is 0.4, which are some of the standard values. Now the first thing is we need to find MR, the peak resonance or resonance peak. What is the resonant peak formula for second order system? MR is 1 by 2 zeta into 1 minus zeta square. So zeta we know 0.4, we can easily substitute here 1 minus 2 into 0.4 under root 1 minus 0.4 whole square, so which gives 1.3535, so which is the resonant peak of the given system. Similarly we can find the resonant frequency. So resonant frequency omega r is omega n into 1 minus 2 zeta square. So usually it is omega d is omega n into 1 minus zeta square in time response. But in this case it is a resonant frequency, it is not the damped frequency. For resonant frequency, inside the square root we have 1 minus 2 zeta square. So we need to observe the disreference. Inside if you have 1 minus zeta square, it is going to be damped frequency. So inside under root inside, if you have 1 minus 2 zeta square, it is a resonant frequency. And this we can assume omega n is at 10 radian per second. For this 10 radian per second, then we can write omega r. So omega r is 10 into 1 minus 2 into 0.4 square under root. So that gives 8.2 radian per second. So this is the resonance frequency. Similarly, we can find the peak time. So peak time is pi by omega d. So we already said that omega d is omega n into 1 minus zeta square under root. So it goes pi divided by we have a 10 under root 1 minus 0.4 whole square. So it gives 0.3432 seconds, which is the peak time of the system.